Hello everyone, and welcome to the cart moving down an incline post lab. This is the lab where we roll the cart down the incline, and we set different positions by moving the photo gates up and down the incline, and then measured the resulting time. So we kind of did this lab backwards of the way that we're graphing it. And we actually did this with the position is the independent variable and the time is the dependent variable. But even so, we're still going to graph it as a graph of position versus time because we want to use the meanings that we learned back in the constant velocity unit. So, we graphed the position in centimeters versus the time in seconds, and notice here that the symbol for position is x, right? One-dimensional motion, if you will. Y is vertical, z is in and out, x is horizontal, versus time in seconds. And when you graph that, you got what is called a top opening parabola. Top opening because the opening's up here, and it's a parabola. It's a kind of that U shape that you've learned in math class. Now technically there is another half to this U over here, but that's in negative amounts of time, which doesn't really have a physical meaning. So unlike math class where you might graph the whole function, here we're only going to graph the part of the function that actually has physical meaning, right? The part with positive times. Now you'll notice here that it's a curve. So unlike when we did the constant velocity unit and all of our position time graphs were straight lines, here we're getting a parabola. So that makes things a little bit more difficult to analyze. For example, it's harder to make an equation or math model of this graph when it's a curve. So now we need to do a process which we learned earlier in the year is called linearization. When we linearize a graph, we take what's on the horizontal axis, the time in this case, and do something to it to make the graph linear. So as you saw in the lab, what you needed to do was to graph position versus time squared. And when you graphed position versus time squared in seconds squared, you got a nice linear graph. And you know it's linear because of the high correlation coefficient, 0.99 something or even 0.999 something maybe. Not only is this a very linear graph, but it also contains the point 0, 0. And as we've seen in many other labs this year, when you graph two variables and they create a graph which is both linear and contains 0, 0, we can say that the two variables are proportional to one another. So this would be read as position is proportional not to time, but to time squared. Now what does that do to the relationship? Well, say for example that we allow the cart to roll twice as long. It's not going to have twice the position. It's time squared. So if we have it roll twice as long, it's going to get to 4 times the position. If we let it roll 3 times as long, it's going to get 9 times the position. If we let it roll 4 times as long, it's going to have 4 squared, 16 times the position. And this is how this relationship works. Now if you think about it, time doubles, position goes up by 4. Time triples, position goes up by 9. Time quadruples, position goes up by 16. So as the time increases, the position increases faster. That's why the graph gets steeper and steeper, because the position is increasing faster than the time. And that's why we get a top opening parabola. We'll see other relationships as we go throughout the course of the year, but this is the one for a cart moving down an incline. Well, since we linearized it by squaring the time, we now can create a y equals mx plus b math model for this linear graph. In this case, the y is what we graphed on the vertical axis, which is position, so that's x. And don't get confused here, this is the symbol for one-dimensional position. So that's why I tend to say vertical axis, because here we're graphing x on the y-axis. That is equal to your slope. Now throw in your slope. Okay, not the one that I'm going to write, unless it happens to be yours. The theoretical slope for a cart rolling down a frictionless 10-degree incline is actually 85. Now again, don't write yours down unless yours happens to be 85. And really we need another unit under our belts before we're going to be able to figure out why this is 85. But one more unit away we'll be able to determine that. You'll just have to believe me for now. The units for it come right from our units of slope. We find a slope by doing rise over run. So the units of rise are, of course, centimeters. The units of run are seconds squared. Now, just to give you a little evidence here that that isn't just some made-up number, let's take a look at the Google form into which you entered your slopes. I have 31 different values here that were entered in back in 2013. And if you look here, the class average or the honors physics average was about 88. 88.327. And if you look at the answers, yeah, they vary a little bit. There's a 70-something here, there's a 90-something there, but you know, they are pretty close to about 88 on average. So of course, that should lead you to some belief here that this wasn't just some made-up number. It comes pretty close to matching what we found here in reality. And we'll talk in a moment about why we didn't get exactly 85 like theoretical. So first of all, let's do a little percent error calculation. Take your slope as the experimental value, and 85 is the theoretical, and find the percent error. That's 85 minus your experimental over 85 times 100 to turn it into a percent. And don't worry about the positive or the negative sign. That's really whether you're over or under the theoretical. If you take the class average, which is an 88, it's about 3.5% error. That's not too bad. Should be pretty convincing that that really works. And in this case, it's a much more complex lab than some of the ones we did earlier. Like we did the force of gravity lab where we just hung masses onto a scale. That one's not too complex, so we would expect it to be a little more precise. This one's a little hard. There are a number of sources of error that you might want to mention in your lab report. For example, we were assuming that this was a frictionless lab, and there's no reason to really believe that it's perfectly frictionless. One of the big ones might be, did I really set up the lab so that it was 10 degrees? I mean, think about it. If it's 10 degrees, if I'm off by a degree, that's 10% error right there, right? Just by being off by a degree. And it's pretty hard to get these set up perfectly. The big one is probably, where did you start your cart? Did you start it right at the top photo gate so that it started the timer as soon as you let it go? If you didn't do that, that might throw in some error. And one other thing, did you actually put the photo gates where they were supposed to be? All of those things might contribute to a few percent error here and there, but hopefully it's still pretty convincing that 85 isn't a number that's kind of out of bounds. Like I said, in a unit we'll be able to actually calculate why that is the theoretical value. So to finish up our math model, we have our y equals m, and now we need our x. Well, x is what we graphed on the horizontal axis. That's not time, because this wasn't the linear graph. We graphed time squared. Plus our y-intercept, but our y-intercept is essentially 0. You can actually check that. The biggest position was 80 centimeters. 5% of 80 centimeters is 4 centimeters. So look at your y-intercept, and my guess is your y-intercept is less than 4 centimeters. Therefore, your y-intercept is smaller than 5%, and we can say it's negligible. That doesn't mean it doesn't have a meaning. Right? This is a graph of position versus time squared. So having a 0, 0 point here would mean that when the time is 0 seconds, the position is 0 centimeters. It's the meaning of the y-intercept. So again, we don't want just the math meaning that it goes through 0, 0. We want to know what it physically means in this case. Since you don't have to add 0, that gives us a specific math model of x equals, or position equals, 85 centimeters per second squared times the time squared. One thing I want you to get here, look at this math model we made. It's got a time squared in it. Because the time is squared, that's why the original graph has the parabolic shape. This is, in fact, the equation of this graph, right, which we got through this process of linearization. I know that's a little weird, but linearization allows us to create the math model of a curve. At least if it's a fairly straightforward curve like we're going to look at in introductory levels of physics. You get into more complex things and you need to use curve fitting or calculus or something like that to do it. But for us, since this is really the most complex curve we're going to see, we can do this process of linearization and create the equation of the curve. Now, one thing I want you to notice, at no time during this post lab did we talk about what this 85 centimeters per second squared actually meant. What does it actually tell you about the motion of the cart as it moves down the incline? The reason I didn't try to get you to tell me that is because we don't know yet. We need a little more physics in order to be able to understand what this slope means. It's going to take us about 2 days, 2 class days, before we have enough physics background to be able to understand this slope. So that's something to look forward to here in the next couple of days. Right? And the next step now is to move on to the movie called Instantaneous Velocity, which is going to give us an idea about how we're going to analyze this graph. Because notice, it's a curve. Right? It's not a straight line. I mean, for example, we know that the position versus time graphs have a slope, which is the velocity. That's something we learned about in the constant velocity unit. But how do we deal with that when it's a curve? How do we find the slope of a curve? Well, that's what the next movie will tell you about. So make sure you watch that movie before tomorrow. And by the way, I want you to just write this into your notes now. Slope equals with a line, because we don't know what the slope means yet. So we're going to come back to it and give you a meaning so that when you write up your lab report, you not only have the meaning of your y-intercept, but you'll have a meaning for this slope. But again, it's going to take us a couple of class days. So please go and watch the movie Instantaneous Velocity.